In this video, I want to run through two examples of sort of your basic proof by mathematical induction question. So our first one is prove that 1 plus 3 plus 5 plus all your odd numbers up to 2n minus 1 is going to be equal to n squared for any n greater than 1. So when we talk about n, we're talking about the natural numbers, so whole positive numbers. All right, so we're going to run through our steps. We already have the statement written right there, so we don't need to rewrite it. But if you were doing it in an exam or in your exercise book, then you would rewrite this statement that we're trying to prove. So our first step then is to show that this statement is true for our smallest value, which is n equals 1. All right, so if we're showing that's true, if we were to substitute n into this part here, we would get 2 times 1, which is 1, minus 1. So we'll just get this bit simplifying down to 1. So if n's 1, we've only got one term in this series. So our left-hand side is going to be 2 times 1 minus 1, which is just 1. Now the right-hand side of that equation is going to be 1 squared, which is also 1. So because our left-hand side is equal to our right-hand side, we can say, therefore, true for n is equal to 1. Our next step is that we're going to assume that that statement is true for n equals k. So we're going to write out what that means. So I'm going to write i.e. that means that 1 plus 3 plus 5 plus all the odd numbers up to 2k minus 1 is going to be equal to k squared. So we're going to assume that's true, and then we're going to say that if that is true, then the next one has to be true. So we're going to prove true for n equals k plus 1. So that means what we're trying to prove is that 1 plus 3 plus 5 plus all the way up to 2k plus 1 minus 1 has to be equal to k plus 1 squared. So we're going to try and prove that this is equal to this one. So I'm going to start with the left-hand side and manipulate it. So the left-hand side, 1 plus 3 plus 5 plus... Now what I'm going to do before I write this one in is I'm going to write in the term that would come directly before it. So if this one had our n equal to k plus 1, then the term directly before it would have been when our n was equal to k, which was just this term here. So I'm going to write in the term before as well. So I've just rewritten this left-hand side, but I've added in one extra term into my notation. Now we know that this whole section here, because we've assumed that it was true for n equals k, we know that this whole section can just be rewritten as k squared. I'm going to write that bit as k squared, and then I'm also going to simplify this down a little bit, so expand that bracket out. So I'd have plus 2k plus 2 minus 1. So if we simplify that again, we'd have k squared plus 2k plus 1. And we know that that's a quadratic and it's a perfect square, so it can be simplified as k plus 1 squared, which is exactly what we were aiming for. We were trying to prove that this statement was equal to that. So we're going to write equals right-hand side. So we've got a couple of statements we need to write. We can write therefore if true for n equals k, true for n equals k plus 1. So we've proved that, that's almost running off the page. We've proved that if this is true, then this one also has to be true. And because we also proved this very first step, that we can push that first domino over, then that means that this statement has to be true for all n, where n is greater than or equal to 1. All right, so that's our first proof finished. Let's have a look at the second one. So our second proof asks us to prove that 5 plus 9 plus 13 plus all the numbers up to 4n plus 1. We need to prove that that is going to be equal to n outside of 2n plus 3. Again, we're looking at all of the natural numbers. So our first step will be show true for n equals 1. So if we were to look at this left-hand side of the equation, when we substitute 1 into here, we're going to get 4 times 1, which is 1, plus 1. So this will give us 5, which again is just the first term in our series. So 4 times 1 plus 1 is 5. And if we substitute into the right-hand side, we're going to have 1 outside of 2 times 1 plus 3, which will also simplify down to 5. So we can write therefore true for n equals 1. So it's the first step in our proof. Then we're going to assume that that statement is true for n equals k. What that means is that if we had 5 plus 9 plus 13 plus all the way up to 4k plus 1, then that is going to be equal to k outside of 2k plus 3. So we've assumed that's true, and now we want to prove that if this is true, it's also going to be true for the next one along. So we're going to prove true for n equals k plus 1. So again, we're going to write the statement that we're going to try and prove. So we're going to try and prove that 5 plus 9 plus 13 plus all the way up until we get 4k plus 1 plus 1. It's going to be equal to k plus 1 to k plus 1 plus 3. So we've just substituted k plus 1 in where all of our n's were originally. So now we need to prove that that statement's true. So again, I'm going to start with my left-hand side, which is this sentence here. I'm also going to do the same stuff I did in my first example, though. I'm going to include the term directly before this one, which would have been my 4k plus 1. We're going to have my 4 plus 9 plus 13 plus, and then all the way up until I get 4k plus 1 plus 4k plus 1 plus 1. All right, so we know again that this whole section is what we had written in this line up here. So this whole chunk is going to simplify down to this. So I'm going to write that as k outside of 2k plus 3. And then I also have this term on the end. I'm just going to simplify that as well. So I'm going to have plus 4k. So I've got 4k. If I expand that out, I'll get 4. And then I've got my plus 1 on the end as well. So I have 4k plus 5. Now, if we want to go through and simplify that expression, I'm going to expand out. So I have 2k squared plus 3k plus 4k plus 5. Collecting like terms, I have 2k squared plus 7k plus 5. Now that's a quadratic, so I know how to factorize that using whatever method you want. But that's going to factorize to k plus 1, 2k plus 5. So I can't really get any simpler than that. So now what I'm going to do is I'm going to leave that alone for a minute. I'm going to simplify this down and see if it comes out to be the same thing. So I'm going to leave my left-hand side. I'm going to go to my right-hand side, which we know is k plus 1, 2k plus 1 plus 3. If I simplify that, my first bracket's just going to stay the same. But if I expand out that second bracket, I'm going to get 2k plus 2 plus 3. So I'll get 2k plus 5. Which is exactly what my left-hand side simplified down to. So that means I'm going to have, therefore, left-hand side equals right-hand side. And then I can write if true for n equals k, then true for n equals k plus 1. Oop, running off the page again. And then we can put our final statement and we can write therefore true for all n when n is greater than or equal to 1. So that's sort of your most straightforward situations where you're solving a statement using mathematical induction.